So in today's video, we're going to look at the topic representation of organic compounds. So there are quite a few methods. So firstly, let's look at molecular formula, which is mostly used. So what it shows is that it shows the actual numbers of each type of atom in a molecule. So when we want to know the molecular formula, we are more concerned with the number of atoms the molecule has. So for instance, if we are talking about butane, if we are talking about butane, so butane has four carbons. So we're rather interested about the number of atoms, C4, rather than actually the structure or the bonds, which is more emphasized on the structural formula. So it's C4, and then you have H, 2n plus 2, that would be 10. That would be 10, right? So C4H10. So we are more interested about the number of atoms, or number of the specific atoms we have, rather than the structure, the bonding. And now talking about the structure and the bonding, uh, we can talk about structural formula. So we are more interested about how the atoms are joined with each other, about how they are bonded to each other. So for instance, for the same molecule, if I am to write the structural formula, what I would do is, as I said a little earlier, that structural formula is more focuses more on the structure, more on the bondings, and how the structure follows. So it would be rather like this: CH3, like we have C bonded to 1, 2, 3, 3 hydrogen, following CH2, CH2, and lastly we have again CH3. So we see that uh, structure formula is more into how they are structured, rather than the number of we are less interested in actual number of carbon. We are more interested in the structure, or how they are organized. So that is the structure formula, which shows how the atoms are joined together in an organic compound. So moving on to a more detailed structure. So the one which I drew at the beginning, very initially, is this. So looking at this, you get the total idea of how many you can visually represent it. Just by looking at it, you can understand how the structure is going and what the structure is. You can see the bonds, you can see everything actually, and like uh, and the definition goes like it is an expanded form of the structural formula, right? So first we have CH3. So expanding it, we can write C H3Hs. So that is a more in-depth more in-depth look into the structural formula. So and you can visualize it in a more better way. So it's formula showing the location and the type of every bond. Moreover, you can also focus on the bonds in an organic molecule. So these are the three. So this is the first, if you're interested on the number of each atoms. So you have molecular formula MF. Then if you're interested in the structure, SF, which is mostly used. And if you're interested more, if you want to have an in-depth look of the structure, you can have a displayed formula. And this is among them, this is mostly used, the structure formula. So you can have all the areas together. You can see the number of atoms. You can see how they are structured, everything in one formula. So structure formula is mostly used. And talking about all this, there is something known as empirical formula. So using this, what happens is we can get the idea of the homologous series usually. So it shows the simplest ratio in which atoms in an organic molecule combine. So for instance, rather than writing C4H10, I can just break it down into this into 2 and 5. So C2H5. Similarly, I could have broken down a C40 or C90 and H, let's say 3000. So I could just keep on dividing by 3 until I could get something very so I could write C9 H30. So similarly I could just keep on until I would get something like this on the lowest form. So that's the empirical formula. So this gives an idea what the structure now which group it belongs to. For instance, uh, by looking at the empirical formula of uh, this, we can say this is an alkane. Already we can say this is an alkane. So that's what empirical formula is. Now something new into this into the A levels, that is this skeletal formula. So skeletal formula is something that looks like this. So it's a simplified version of the displayed formula, and it's called the structure formula. And every carbon represents a so in here every kink or every change in the straight line shows a carbon, and carbon bonded, and what is this one, what goes on the other side is that, so each kink is a carbon, each bend, each corner is a carbon, and we consider that they are totally surrounded by hydrogens. So here is a carbon, here is a carbon, here is a carbon, here is a carbon, and they're surrounded by maximum number of hydrogen. Unless uh, unless there is something else. For instance, if there is for here, let's say instead of an hydrogen, there was something else, which is the OH. So what you do, you have to draw an extended line. So this is an extended arrow, and this doesn't have any carbon. Rather, uh, this is an extended line to show that there is another molecule. So this is the catch. This is the only catch you can have in the structural formula. So we will have a better look as we go more into the details. So first of all, we talked about the molecular formula. So for instance, let's talk about butane here. So we have the molecular formula of butane, C4H10, which is the molecular formula. We have the number of carbons atom, we have the number of carbon atoms, and we have number of hydrogen atoms all together. Nothing about the structure. So that's the just the molecular formula, and this is the displayed formula showing how the butane actually is. We have single bonds, single carbon bonds, and all of them are surrounded by hydrogens. So first of all we have C at the end of the chain, which is bonded to three other hydrogens. So we have one carbon bonded to three other hydrogens. Similarly, we have second carbon bonded to two other hydrogen. So second carbon bonded to two other hydrogen, and that's how it goes, like in the sequence. And we have the structure formula. Moving on to another example, we have four carbons and we have double bonds. So this is a butene. That's an alkene, as we have a double bond. And one thing you can note that is in structural formula you can show the double bonds. You can actually show the double bond in the structural formula. So it's CH3, CH, 1H, again 1H, and it's double bonded carbon. And lastly you have CH3 again. Here, you write it down here, CH3. Moving on to more other things. So, for instance, uh, instead of a hydrogen at the end, at the start or the end, at the end of the molecule, you have a group or you have an atom. So what you can do is you can write it in two ways. Uh, we know so the carbon, this carbon is bonded to a boron. Here is bonded to a boron as well two hydrogens, as well as two hydrogens here. So you can write it like that, that a carbon is bonded to boron and a hydrogen. However, you can also write if the boron is at the at the start of the chain, so you can write it in two ways. Whether you can show that the boron is also like combined, or the boron is attached to the carbon, and also the hydrogen is attached to the carbon. So you can interchange the carbon between so if the bromine is at the beginning of the chain, so what you can do is the hydrogen and the carbon can interchange, so you can write it in both the ways. Moving on, uh, so in the middle, this is something really important. So for instance, if you have a bromine here and you want to show this bromine belongs to this carbon, what you do is you write the formula and put a bracket in front of bromine, which means that it belongs to the previous carbon. So we have CH3 here, we have three hydrogens, then we have another carbon which is bonded to bromine. To show this bromine belongs to this carbon, you put a bracket, which means that it belongs connected to previous atom. So an OH here, and it's in a bracket, this means it's for the previous atom rather than the front one or the other one. So this means a bracket, you can silently say it means bonded to the previous atom shown. So we have a CH, so we wrote a CH, and then we have a OH which is bonded to this carbon. So to show this, you put a bracket after writing a CH and OH to show that it's bonded to this carbon. Moving on, let's look at a complex one. So first of all, we have C and three H's. I have omitted the H's for simplification, so we have three CH3. Then we have CH and a Cl group. So what did I say? To show that the Cl belongs to this carbon, you just have to put a bracket and write the Cl. Then we have CH. As we have a double bond, we have only one H, so we have CH, and then a double bond, so we can just write we can just put a double bond. Then we have a carbon, again CH, and we have a C double O bond. So we can do two things. Let's move on. Like, how do I shift it? Let's just move on like this. So after CH, you can do two things. That so after this we have this part remaining. So next you can write C double bonded to O. You can do this, or like I have written here, you can write C double bonded to O, or you can just write CO. You can do this, or you can just write CO. Either way is fun to show the double bond. You can actually show the double bond, or you can skip it. Then you have to write CH2 for this, and then we have OH only. So you might put a bracket in, and it's better not to put because it's at the end and you have to show which carbon it is bonded to. So you can just write OH, and that's it. Now moving on to the skeletal formula. So what we talked about is that every kink, every starting, every ending, and every kink shows a carbon atom. So can you see? So here's a kink, or here is a starting. Every point, every corner shows. So every kink or every corner can show a carbon atom. I will talk about exceptions later, but that's another part. So you have one carbon, so you draw one kink. So we start. Let's start. So one carbon, one. Oh, let me do it more in a straighter way. So I have one carbon, so I draw one line. And here is my first carbon. And for this second carbon, let's put another kink. So this represents another carbon. And again, so this kink can represent this carbon. And we have the last ending, so we don't have to put anything here. So this carbon is represented by this ending. So we have corners. If you count corners or kinks, uh, so we have 1, 2, 3, 4. So 4 carbon, 4 kinks or 4 corners or 4 whatever you say, like the endings or the uh, where you shift the line, straight line. So total, including the starting point and the ending point and the corners, we have 4 such points and we have 4 carbons. So that's how you represent, and you don't have to write the H's in the skeletal formula. The only other thing that you don't need to write is the H's. So we consider that this carbon is at the first, so it's bonded to 3H atom. So CH, and we know that there is also a C here. So the C is in the middle, so it is bonded to one carbon. Here is bonded to the second carbon. It can have 2 more bonds, so CH2. Similarly, this is also CH2, and the last carbon here CH3. It can again have 3 such bonds, so it's CH3 again. So we see that it's a simplified way of representing the skeletal form, the structural formula. Moreover, you can also show double bonds. For instance, if we had a double bond here, we could show a double bond like this as well. Pretty easy, right? So moving on to the more in-depth look, let's have an in-depth look into the skeletal formula. So any end line also shows C atom. So this ends also represents C atom. We know this. Now there are two conditions you have to look at. That is that, uh, so I said for both of them, I said every kink represents a C atom. So this kink represents a C atom unless the condition is, let's say, uh, the structural formula was O and there was no carbon in the middle of the whole thing. So what should you do? You just have to literally put a O here instead of the kink. You have to put an O here, and the structural formula would go like this. So it would look something like this. So instead of a whole kink, what you do is you give a space here, write a O, and again start the second line. So what it means is you have one carbon, you have second carbon, but you don't have a carbon here. It's replaced complete. When it's completely replaced, it has to be completely replaced by another atom. So and there is a space that it's not connected. So it represents that it's just connected to the carbon, and you don't have any carbon. There is no kink actually, right? So that's that. And the other thing is that at the end line it shows a C atom. So what I said is this ends also represents carbon atom unless there is anything present. So for instance, you write let's say uh, let's say it didn't end in let's say we put a OH here, so that it becomes an alcohol and we have one less H and an OH atom bonded. So now if you put an OH atom, let's put it at the beginning. and if we write a OH, so this end doesn't contain any carbon, this end. In the beginning I said something as an extended line and extension. Consider this as not as a kink or any corner, just consider this as an extended line, EL, an extended line, which represents nothing. I mean, it doesn't have any carbon at the front. It just have the OH, which is just shown by an extended line. So this doesn't contain any carbon. So that is the thing. And the last point is which I already just said. An extra atom are shown by. So if there is an OH, let's say at the let's say there is an OH or there is something to be shown. Uh, it's not just only a simple hydrocarbon. You have other groups or other functional groups. So what you can do is you put an extended line and that corner doesn't represent any carbon. So for instance, uh, if I have to show that an OH atom is connected to this carbon, I have to write an OH and I have to extend the line from this carbon. This is pretty confusing because sometimes what I used to think was that there must be a carbon here because this is a corner, but that is actually not, because this is an extended line. You have to consider this is an extended line. Whenever you see there is an other type of group or other type of atom is attached rather than carbon and hydrogens. So it's just 1, 2, 3, 4 carbon, and this line actually represents nothing but an extension, which means that OH is connected. So moving on, we have CC, we have 2 carbon, and which are double bonded. So to represent this, we have to write so one corner represents 1 carbon, another carbon is in the kink. So this is a carbon, this is a carbon, and again there is another carbon, the third carbon, which is connected to the Cl. But we have a double bond here, so we can show the double bond through this. So this is a double bond, and the Cl is connected by an extended line. So this is an extended line. So there is no carbon here, rather it's just an extended line to show there is another carbon, there is another kind of atom that is located, that is situated here. So moving on, we have CH2, nothing attached, no atom attached, so we have CH2, and at the end we have another carbon. So here is the carbon and it ends. So this is an extended line, this OH. So this is shown by an extended line, and also the double bonded carbon is also separately shown. So we know there is no carbon here, and the chain ends here and starts from here and ends here. So these are just extensions. These lines are extensions. So moving on. So as I said, at the beginning corner, and any corner might show a carbon atom, but we see a Cl is in the front. So we start off with Cl, and we see this is an extended line. This is not a carbon. The carbon actually starts from here, and the Cl is connected to the carbon. And in the second carbon, we have a double bonded O. So we show that through arrows, through extended lines, through 2 extended lines. Moving on, we have third carbon connected to the fourth carbon as a double bond. So we show the double bond. Then we have the 1, 2, 3, 4. We have the fifth carbon connected to one OH. So we an extended line. Using an extended line, we show an OH is connected to the fourth carbon. And finally, we have the fifth carbon here, and we don't have to show the H. We know that the H we don't have to show. So the double bonded oxygen we represented like this. We drew extended double lines to show they're connected to the carbon. So let's look at a few other examples. So for skeletal formula, each straight line end, so this ends and every corners, every kinks represents a carbon atom. Yeah, we just got to know that. And it's assumed that the other bonds of carbon is filled up by hydrogen, right? Yeah, so we just drew the kinks and the corners, and we assume that they're filled with hydrogens. So if I zoom into this, shit. So if you can have a look, that we think that these corners are actually carbons which are filled with which are surrounded by lots of hydrogen. I mean, they're full with hydrogen. So this is another carbon, this kink, and they're surrounded by hydrogen. The maximum number of hydrogen that can be bonded is actually bonded to this. And at the last carbon, it has one bond, so it can have three more bond. So 1 2 3, H H H. So the last one is CH3. As we can see, it matches up with the structure formula CH3. At the beginning you also have CH3, so it's CH3, and we have two more kinks, one here, one here. So we have two more carbons, one here, one here. That's how it goes. So moving on, this is basic period. This is also easy. 1 2 3 4 5. So we must have five kind of bending and corners together. So 1 2 3 4 5. We can see a double bond in the third, starting from third carbon. So 1 2 3. So in C3 we have a double bond, and there is no extra, nothing extra attached. So let's say there is not CH2, rather there is CH and a Cl atom. So what do? So in the second carbon, you put an extended line like this, and you put a Cl. So this corner represents nothing but an extension, which means that a Cl atom is attached to it. Moving on, we see that we have 1 2 3 4 5 carbons. So we must have five kings or five corners and five endings, five such points. So we have 1 2 3 4 5. So we have five kings, and we see double bonded O. So we have a double bonded carbon atom in the middle, which means it's a ketone group. So it's in the second carbon. So 1 2. So using extended arrows, using two arrows, we represent the double bond. Now something complicated we have, that is, in the middle of the carbon, in the middle of the chain, we have Cl atoms, and this bracket, as I already said, represents that this Cl belongs to this carbon, the previous one. So this is carbon 2, and if you look, that 1 2, in the carbon 2 we have an extended line, and we show the Cl atom. So that is how it goes. And if it's at the end, we also draw like 1 2 3 4. We have four carbons, and we have 4 1 2 3 4, four kinks, and the last one is actually an extended line. This represents nothing but an to show that something rather than carbon is bonded to it. So don't confuse it with a carbon. Don't say that there is a carbon here. There is nothing except the hydroxide group. That's how it is. And I think we could end it here, and we shall see you next class. Bye.